Well, greetings. It is a beautiful day to study some mathematics, my calc babies. So chapter 8, section 7, and the topic is on indeterminate forms. Indeterminate forms and a new rule for approaching them, what we're going to call L'Hopital's rule. So let me begin with what we know at this point, right? So take a look at the two limits that I've produced here. And let's think about how we were able to approach limits prior to, or at least let's say back in Calc 1. So the idea was pretty simple. If you we're able to, so for example, in this case, we're taking the limit of 2x squared minus 2 over x plus 1 as x approaches negative 1. So probably the way you were taught is it's worth trying to see what happens if we simply use a substitution method, right? So if we can use tables, we can use the delta epsilon definition, we can even use graphs, but for a more analytical approach, we start off by just seeing what happens as we plug in negative 1, right? Well, if you plug in negative 1 into that function, we would get 0 over 0. Right now, 0 over 0 is what was defined as an indeterminate form. And in other words, it cannot be determined whether the limit exists or not. And if it does exist, it doesn't give us any information as to what the limit is. Now, likewise, if I jump to the second limit, if we take the limit, this time your x value is approaching infinity. And well, although this is kind of sloppy, but if you think about infinity squared times 3 minus 1, I think we can agree that we're still at infinity. And likewise, we're still at infinity in the denominator. So 0 over 0, infinity over infinity, these are both, again, considered indeterminate forms. So we cannot determine if the limit exists from its current form. So, well, what were some techniques that we were able to use back in your previous calc classes? Well, one technique, and these were both algebraic techniques, was to try factoring, right? And then we hope that through this process something cancels. So let's go ahead and rewrite this. So we could think about this question as the limit and then x is still approaching negative 1. Only now we can factor out the 2, leaving us with x squared minus 1, which is just x plus 1 times x minus 1. The denominator is fully factored, so that leaves us here. So now remember, to divide by 0 comes in two flavors, right? It is either, now I'm just throwing up a random graph. This graph has nothing to do with this function. But if you're dividing by 0, that means that you either have a vertical asymptote at the x value, say negative 1, or you have a hole in the graph. Right? So that's getting a little bit cluttered. So let me try that again. So either you have a vertical asymptote or you have some type of hole that is in your graph. All right, now, what am I trying to say to you? I'm trying to say that if you're trying to divide by 0, division of 0, then that means something geometrically. The geometry of that is basically telling you that either your function is approaching some vertical asymptote, leading you to divide by 0, or your function has a hole somewhere in the graph where your x value is undefined. Okay, so now think back. When it comes to limits, if you recall, so limits can exist at holes, right? We can say that the limiting value exists. We could say that f is approaching the same L from both sides as x approaches c. However, limits do not exist at vertical asymptotes. So at this stage of, if we go back to our problem, you and I, we know that you cannot choose -1, right? That is for sure. That is not part of the function. It's not a y value that is defined on your function. What we don't know at this point is whether that is a hole in the graph or whether that is a vertical asymptote. Now, because that you're seeing that we have an x plus 1 in the numerator and an x plus 1 in the denominator, that is telling us we have a common factor. So when we cancel out that common factor, what is left at that point is just the limit. X is still approaching -1, but now what's left is just 2 times x minus 1. All right, and this function we actually can use that substitution method at this stage of the game. We can substitute in our -1, and which tells us that we have -1 minus 1 times 2, which is -4. So notice we began this limit with 0 over 0, which was indeterminate. We did not yet know if the limit existed, nor did we know if it did exist what it was. Using some algebraic techniques of being able to factor and cancel like factors, we were able to determine that yes, the limit does actually exist. It is a hole in the graph, and that is and the limit is -4. Now, looking at the second example, so in this case we have the limit as x approaches infinity. Okay, and when we do try to use direct substitution, whatever it would mean to substitute infinity, whatever that statement actually means, but when we try to use our direct substitution, we do end up with the statement infinity over infinity, which again doesn't give us any information. It's not equal to 1. Okay, it is indeterminate whether the limit exists. So one method here, of course you can there's different ways of approaching this, but one of the methods you probably learned was to divide the numerator, so every term in the numerator, and every term in the denominator, so divide both the numerator and the denominator by the highest power in the denominator, right? So let's look at the denominator. The highest degree in the denominator, I think I said power a second ago, is the x squared, so we're going to divide everything by x squared. Ready? So let's rewrite that. It'll take me a second. So that means if I divide the numerator and the denominator by x squared, I have 3x squared over x squared minus 1 over x squared divided by 2x squared over x squared plus 1 over x squared. All right. Now, clearly, so let me come on over here. So we have a little bit of reducing that we can do. A little bit of simplifying. So these x squareds are going to cancel, as are these. So that leaves me with 3 minus, well, let's think about this. So I'm gonna go ahead and put this infinity in there for x. I guess I can write infinity squared if you would like me to. And let me go ahead and, so now I'm in the denominator, so 2x squared over x squared. The x squareds cancel, leaving me with just 2. And again, just for the purposes of teaching, I'll go ahead and put my infinity here and square it. All right, so first off, what does it mean to divide something up an infinite amount of ways, right? So intuitively, let's think about you have $1, and you are so generous that you are willing to share your $1 with an infinite amount of people. Well, if you share your $1 with 2 people, each would get 50 cents. If you share your $1 with 10 people, each would get 10 cents. But as you continue to divide your $1 more and more and more, each individual is going to get less. So that we can make the statement that if you're going to divide up some constant an infinite amount of ways, well, how much money are we going to get? Right? You got $1. You start to divide it up an infinite amount of ways, whatever that means. Well, no one's going to get anything, right? It just becomes 0. Hope that it makes sense. So that leaves me with the following: 3 minus 0 over 2 plus 0. Or in other words, 3/2. All right, so these were some algebraic techniques. And some of the other techniques that you would have learned were, say, rationalizing the denominator, or maybe using some special trig limits to redefine and rewrite your functions. But all in all, let's just go ahead and get to the point. These algebraic techniques are perfect if indeed you're dealing with algebraic functions. But what about if you're dealing with non-algebraic functions? So I'm going to erase. Let me see if I have any space on the next page. I do. Okay. So what if we were dealing with non-algebraic functions, right? So transcendental functions. So let's say for right now, let's say you wanted to take the limit as x approaches 0, and now let's actually make our function non-algebraic. So something like e to the 2x minus 1 over e to the x minus 1. Okay, so first things first, you can always try direct substitution, right? It doesn't matter if it's algebraic or transcendental, you can always try to plug the 0 in for x and see what happens. Now in this case, if you plug 0 in for x, we would have e to the 2 times 0, which is just e to the power of 0. Anything to the power of 0 is 1, so we end up getting 1 minus 1 in the numerator, and of course e to the 0 minus 1 is again 1 minus 1 in the denominator. So do you see how we're getting this 0 over 0 indeterminate form? Now, sometimes you can use algebraic techniques for non-algebraic functions. So for example, I actually can factor that numerator. E to the 2x minus 1, that's just the difference of two squares. So that's just e to the x minus 1 times e to the x plus 1. All right, and that's still over e to the x minus 1. So in this case, we actually can cancel the e to the x minus 1s, leaving us with the limit as x approaches 0 of what? Of e to the x plus 1. All right, and now we were able to use this factoring technique, this algebraic technique. E to the 0 is 1, so that just becomes 1 plus 1 is 2, and we were able to find the limit. But this is a very special case. And the majority of the time, this technique is not going to work. So we're gonna need a different way of approaching this. And now I'm going to go ahead and introduce to you this new approach. And what I think you're going to like it. My students are normally never extremely happy about limits, but of all the things to know about, although it should go without saying that there is all those derivative formulas that you hold dear to you, those recipes that you know how to do, they are all born out of that delta epsilon definition of a limit, right? So someone has put in quite a lot of work to save you from calculating limits when doing using limits when doing your derivatives. Somebody saved you quite a lot of time by creating all those little recipes that you learn when taking derivatives. But they all can be done with a limit. Now, what we're going to do is I'm going to introduce to you a new way of doing limits that is it's going to make it much easier. And all that is required is that, so bear with me here. So let's assume that this right here is what you're trying to take the limit of, right? Some quotient, f of x over g of x. So the rule, which is known as L'Hopital's rule, says that, look, well, why don't we just take the derivative of the numerator, then take the derivative of the denominator, and then try taking the limit as x approaches c. Right? So I offered this to you without proof. Where I think what we'll do is we'll go through just the how-to, and we'll use the exact same examples that we used on page 1, okay? So L'Hopital's rule. So L'Hopital, just a mathematician. This is, my gosh, let me try. My math history is starting to wane on me. So probably about 1860. That's no, 1660. Is my guess, somewhere around 1650, 60. Somebody should always fact check me. I do know, just a little bit of trivia. I know that L'Hopital was credited for the very first textbook ever used, the very first calculus textbook. And if I recall, this rule, this L'Hopital's rule that he is credited with, was a little bit of controversy as to whether this really was his rule, or if it was because he was tutored by one of the Bernoulli brothers. I think it was John, if I recall. And of course, since he was tutored by John, he purchased his notes, and then he took so basically he purchased the rights of his material, if I recall, and then built a textbook out of his material, and in that textbook was this rule. And L'Hopital got quite a lot of credit. Now, whether anything I just said was correct or not is for someone else to fact check, because I do not place any salt into any of these little tangents that I go on, because it's just coming from memory. All right. So, but how do we apply this rule? So let's go back and let's go ahead and try this new approach. So L'Hopital's rule says let's go ahead and take the derivative of that numerator and the derivative of that denominator. So we'll go ahead and do that right now. So the derivative of 2x squared minus 2 is just 4x. And the derivative of x plus 1 is 1. Okay? So now, you're not done yet. Now we want to take the limit as x approaches negative 1 of f prime over g prime, right? Over the derivative of the numerator divided by the derivative of the denominator. Which we can see, if you plug in negative 1, we're just going to get 4 times negative 1, or negative 4. Which, if you look back on the previous page, that was exactly what we got previously. Right? Okay, so not bad. So let's try this. Let's try this L'Hopital's rule on the other problem. So again, let's go ahead and take the derivative of the numerator. So I'm just going to, for f prime is going to go on top, g prime is going to go on the bottom. So the derivative of 3x squared minus 1 is just 6 times x. And the derivative of 2x squared plus 1 is just 4x. So we're now going to rewrite this problem as the limit as x goes to infinity of 6x over 4x. And of course, those x's are going to cancel. Right? So that means we have the limit as x approaches infinity of 6 fourths. Right? So these x's canceled. And 6 fourths reduces to 3 halves. And look, there is no, if you take the limit of a constant, it's just the constant, right? There's, in other words, there's nowhere to plug this value in because all of our variables are gone. But the good news is what's left, the constant 6 fourths, which reduces to 3 halves, is exactly what we got in the previous page. So not bad, right? This is not that bad. How can I make this harder on you? Well, first let me do this. First let me start with the most common mistake. Okay, so I'll spend just a second pointing out the most common mistake. And then I'm going to introduce to you some new indeterminate forms, right? There's more than just 0 over 0 or infinity over infinity. There's other indeterminate forms that we'll discuss in just a second. So first, though, the most common mistake. Okay, so notice that L'Hopital's rule is what I'm boxing in right now. It's saying that the limit as x approaches c of some f of x over g of x is equal to the same limit as x approaches c of f prime over g prime of x. It is not, notice, it is not the same as taking the derivative of the quotient. Okay, so it's the quotient of the derivatives, not the derivatives or the derivative of the quotient. Now, don't let me lose you. What I'm saying is you're not ever going to use the quotient rule. It's not that. You take the derivative of the numerator, then you take the derivative of the denominator. Then you evaluate the limit. Never the quotient rule, okay? It's never this f prime g minus f g prime over g squared. You're never ever going to use that, okay, when you're applying L'Hopital's rule. I shouldn't use statements like that, but that is the most common mistake. You're not going to use that quotient rule. All right, so now what are some other indeterminate forms? So, and then how do we use this L'Hopital's rule moving forward? So look, we've already discussed 0 over 0, infinity over infinity. If when you're evaluating a limit, both of those forms are indeterminate. They don't tell you any information. In other words, you have to roll up your sleeves and do some more work to figure out what the limit is, if it even exists. But both of those allow for the application of L'Hopital's rule. Okay? Now, some other indeterminate forms. Well, some of these might look weird to you. You might think, well, how is that indeterminate? Right? So if I said 0 times infinity, that is a meaningless proposition when you're trying to evaluate a limit. 0 times infinity is not 0. 1 to the power of infinity is indeterminate. 0 to the power of 0 is indeterminate. Infinity minus infinity is indeterminate. Although what might seem intuitively like, well, anything times 0 is 0, or infinity minus infinity is 0, or 0 to the power of 0 is 1, or 1 to the power of infinity is 1. All these are intuitive. You're taking natural intuitions that apply almost in all circumstances, except when you are trying to evaluate a limit. Okay, because the limit is different. It's the question of what L approaches as X approaches C, right? So then the trick of this section is to take all of these other indeterminate forms and make them look like 0 over 0 or infinity over infinity. Because once you do that, then you can just apply L'Hopital's rule. So notice what I'm saying over and over again. I'm saying rewrite in 0 over 0 or infinity over infinity form to apply L'Hopital's rule. That is the game. So where do we go from here? Well, I do want to take a second and make sure, make sure I point out that why something like 0 times infinity is indeed an indeterminate form, right? I mean, because intuitively we would think that anything times 0 should be in 0. So I'm giving you two different problems here. Okay? I have 1 over x times x, and I have 1 over e to the x times x. So I'm going to come back to the geometry there for just a second. But look, if I were to evaluate the limit as x approaches 0, well, so think about it. 1 as x is approaching 0, both of them lead to infinity times 0, and 1 over e to the x as x is approaching infinity leads to 0 times infinity. So if indeed it's correct that anything times 0 is 0, then we would expect that the answer to both of these would be 0, right? That would have to be true for all statements of infinity times 0. But take a look at the geometry. The limit as x approaches 0 of the first problem, right? This is the green line. We're seeing that the answer to this limit is actually 1. Whereas in the case where that limit x is approaching infinity of the second function, we're seeing that L is actually equal to 0. So the true answer to this is the limit is 1 and the limit is 0. So although both of them take on the form of infinity times 0, 0 times infinity, the result is different. So that is in mathematics, if you get two different answers, you can both be wrong, but you cannot both be right. As long as we have the same assumptions, either both statements are wrong, but they both cannot be right. So that is why we say that even something like something times zero, infinity times zero, I should say, is still indeterminate. It does not determine the value or the existence of the limit. So I hope that that little aside helps you with some of this new notation. And I think there's nothing left to do except jump in and start doing some L'Hopital rule. So I think what I'm going to do is I'm going to go ahead and stop this video right here, and I'll come back for the second part, and the second part will just be churning out some examples, one after the other. We'll go through and we'll apply L'Hopital's rule over and over and over again. The trick is always being able to get it into 0 over 0 form or infinity over infinity form so that you can use the new rule.